Okay, so here we are, sun triangulation part two. And I think you're going to find this real interesting. And after we did part one, if you want, you go back and check it out. Glenn, a friend of mine from West Virginia, he helped me triangulate the sun again. So here's our results. Take a look. First of all, I'd like to say we're not claiming anything. We're taking observations and we're learning. Now, what we're trying to do is we're trying to line up Michigan, me in Michigan, Glenn in West Virginia, and then the sun. We're trying to line them all in a row so we can triangulate it to see how it fits in the sky, to see the distance of it, how it fits on a flat Earth. Maybe we could come back later and see how it works on a round Earth. Okay, so here's our flat Earth map, and in order to line up the three positions, we chose 11 o'clock, September 2nd. And no clouds. That's kind of a tough one too. Okay, so here's our flat Earth map. Let's see where the sun is at September 2nd at 11 o'clock. Now, first thing I did was I wanted to find south from Michigan because that's where we're shooting from, which is about right there. And here's our noon line, basically south. But since it's daylight saving time, this is 1 o'clock. So here's our 12 o'clock line, and here's our 11 o'clock line, right there. Now, on June 21st, the summer solstice, the sun is on this pink line right here. And then it takes 3 months to go to the equator, which is right here. So basically you got 2 and a third months. So you got June 21st, July 21st, August 21st, and then August 21st to September is 9 days, plus 2 more is 11. So you got 2 months and 11 days, 2 and a third plus a day. So from the summer solstice to the equator, which is right here, is about 30 millimeters. And so 2 and a third months would be 10 millimeters would be 1 month, 20 is 2 months, and 1/3 would be 3 and a third. And then we're going to add another day, which would be another third, whatever. So close, somewhere around there, splitting hairs here. So if you look, we're pretty close, 23 millimeters. So that's where the sun should be at 11 o'clock, September 2nd. Now here's Michigan, right here, and here's West Virginia. And let's see how it lines up. Okay, here's Michigan and West Virginia. We line them up. It's a tiny little map, and you can see we're not too far off. Okay, now let's compare our triangulation with dateandtime.com. It looks like we're pretty dang close. So Glenn and I both made right-angled triangles out of wood, and we set them up level so we can measure the shadow, the angle to the sun. Now, Glenn and I are 269 miles apart, and Glenn is like 1,100 and some feet above sea level, and I'm around 700 feet above sea level. So here's what it looks like on CAD. And the moment you've been waiting for, if you look at our calculations, we're 2,255 miles away from where the sun should be straight up and down. Okay, let's see how our triangulation worked. So let's see what the distance is from Michigan to the sun on our flat Earth map. Now, from what I understand, at the equator, which is right here, it should be 900 miles. So on this map, 900 miles is 30 millimeters. 30 millimeters again. Kind of interesting. From the summer solstice to the equator is 30 millimeters. So from the equator to the winter solstice is 30 millimeters. So maybe there's some sacred geometry right there. I don't know. Anyway, so let's measure. So that's 900 miles right there. So let's measure from Michigan to the sun. There's Michigan, real close. Let me check it again. Michigan right there. Yeah, real close. So 68.5. All right, so let's see how many miles that is. Okay, let's use the handy dandy calculator. And we got 68.5 is our measurement, and we're going to divide that by 30. Get 2.28, and we're going to times that by 900. And boom, 2054. So we're off like 200 miles. That's not so bad. I don't think 200 miles is so bad. Using the tools that we're using and everything, I think it's within a margin of error. So I think our experiment went pretty well. Our observations seem to work, within a margin of error. Obviously, we're not perfect here. Only being off 200 miles in this situation, I think is pretty impressive. Now, I would love to, if anybody wants to help, we can do some more triangulations, maybe from other parts of the world, or like somebody like on the other side of the equator. That would be awesome. So let me know if any of you guys want to participate, or if you want to do your own and send me the link. So that would be great. Okay, let's take it one step further. Okay, so let's get this out of the way. Now, here's the sun on a flat Earth map where we calculated it at, and let's compare it to dateandtime.com. Dateandtime.com. So we're gonna go straight up from this light, from where the sun is, and say to about there. Okay, now let's compare this to our dateandtime.com. Okay, now let's compare our daylight on our flat Earth map from where the sun is compared to timeanddate.com. Now, I don't think timeanddate.com can lie about the daylight, because if they said it was dark in one area and you checked it was light, obviously it would be wrong. So I don't think they can lie about that. So when you compare them to each other, I mean, look at them. Look at what's lit up on both sides. It's pretty impressive. It matches pretty well. Okay, now let's take a look. Look to the right of Africa, right here, which is Madagascar. And then look on our flat Earth map. It's lit up right on the edge, same thing. Now look at the light goes all the way to India. Now let's look on the flat Earth map. It goes all the way up to India. And Alaska is lit. So it matches very well. Okay, let's look at it on a globe. So here's our sunlight. And we have the camera set up right in the middle where the sun should be. Now, okay, so here's our day and night line right here. Now let's crank it over. Look how much short we are of India. Look, a few thousand miles short. And here's the line here. Madagascar should be in the dark too. But it's not, so that's a problem. Let's line it back up in the center again. Right there. Okay. Here's the dark on this side. Crank it around. Look at Alaska should be dark. So the problem, it's day and night doesn't work on a globe because the sun will have to go around it. So it doesn't make sense to me. And I don't know if it makes sense to you. Okay, this is the ISS supposedly from space. Look at that sharp line on the left side there. Look at that. All right, let's cruise up to like sunrise. There we go. Some green stuff. I don't know where the green stuff came from. The Aurora Borealis. Okay, and then here's this sharp line. Sharp line on the globe. It should be shining around the corner like 2,000 miles. I want to go what? Okay, I might have got a little bit carried away there, but it seems pretty obvious to me that the day and night doesn't correlate on a globe. There's too much area that's not being lit up on the model. So also I'd like to say is I always thought the sun was like the apparent position, like we always all see it in a different position, kind of like a reflection in the water. But now I'm not so sure because the measurements don't seem to be too far off, and the sun has to be in this position to light up the earth at the right time. So what I'm thinking is maybe what I thought was the apparent position is actually the real position. So I'd love to see more data, to prove what I'm talking about. And if anybody wants to help me do another triangulation, that'd be awesome. Or if you want to do your own experiment, I'll be happy to repost it.